Hello, Flat Earth researchers, debaters and debunkers. Just as we know that geometry has been used to create or describe this image of a circle on the screen, we know that geometry has been used to dictate to us the size and shape of the Earth. But if we ask ourselves a really simple basic question, how big is this circle? We know that really it can be any size you want. The circle is divided up into degrees. We know that there's 360 degrees in a circle. If we divide it in half, we know that there's 180 degrees on either side. The distances between any 2 points are arbitrary. You can measure them on any scale when you have a circle, and the angles will always ultimately be the same. So we have to ask ourselves, how has the shape of the Earth been dictated to us using geometry? Has it been by measuring any kind of curvature on the surface? Or has it been by making observations of the sky? And of course we find that from Eratosthenes to all the other people who have made calculations about the size and shape of the Earth have been done by looking up from the surface into the sky. And this of course is governed by perspective, our dome of perspective, which we will see is just like a semicircle. And this, I believe, is what has been translated into an imaginary globe Earth. Our dome or globe of perspective has been translated into a curve on the surface, simply by having us look up at the sky and translate the angles at which we see things in the sky into the angles that comprise a circle or a semicircle. When geometry is used in this view of the Earth that we've never had, this external frame of reference which translates all the observations we make on the surface into the sky, the use of angles is very handy, and we can make the Earth any size we want, really, but the angles will never change. We can have the globe taking up this entire circle here, or we can make it even smaller, and we can make it smaller still. But one thing that will never change is the angles that are used when referencing the Earth like this. For example, if we put an angle here of 45 degrees and then we increase the size of the Earth, the actual size that we're talking about makes no difference to the angles. These measurements here between places on around the edge become arbitrary. You can have whatever distance you want and then translate it into a circle, because you're using degrees that never change. This will always be 45 degrees from the center, no matter how small or large your Earth is. Yeah? It doesn't make any difference. So you can have the Earth any size you want when you talk about it in terms of angles, using this exterior frame of reference that, again, we've never had and are told to believe that the images we are given of the Earth from space are real. That's all we have to go on as proof. Just some pictures. So we're told that hundreds of years before the technology existed to create CGI images of a globe Earth, or to take a picture from an aircraft through a round window, that the Earth is most definitely a globe. By converting the observations we make of things in the sky, such as the sun, moon and stars, into this spherical Earth from a side-on point of view. Again, a view that we've never had, can only be imagined or assumed when we use the same geometry and angles that are used in the perspective of observations that we make on the surface of the Earth. And we'll see how when those observations are translated into a globe, we end up with this axial tilt that has to be included in the globe, because this amount of degrees goes missing in the conversion. It's lost in the translation from the observer's perspective looking up at the sky into this perspective of the Earth. We look across a flat surface, but we're told we're looking across a globe, so this has to be added to the globe to compensate for the flat surface that we see. This, we see just a level surface, but the angles at which we see things descend towards the horizon is somewhere in the region of 23.4 degrees. And this means that we can put the sun, moon and stars anywhere we like along these lines, and they will always be the same angle, but the distances are arbitrary, just as the distances across the surface of this sphere are arbitrary. They can be put wherever you like when you create a model like this. Again, a model that has been based on observations of things in the sky. That means perspective has been translated into a spherical Earth. Testament to the fact that perspective is translated into an imaginary curved Earth is that of astronomy, in which we look up at the sun, moon and stars, and we're told to imagine them as being in a celestial dome, a semicircle above us, and our horizon is this celestial horizon at 23.4 degrees above what we would be told is the equator on a spherical Earth. So again, we have observations of things in the sky being made from this point here up above us, and still on a celestial sphere that goes all the way around 180 degrees. So we really do have the use of perspective and the idea of a dome of perspective being used to dictate the shape of the Earth beneath our feet. When there is no need, we have a flat surface, and we see things go up from the horizon, over our heads, and then back down again in our own dome of perspective, or our own celestial sphere or hemisphere of perspective. So because geometry is used to convert these observations into the idea of a spherical Earth, this axial tilt of 23.4 degrees or thereabouts can be used on a local level as well. It's just scaled down. So let's just take it off there, and keep in mind that a semicircle is 180 degrees on either side. So for an observer on a flat plane, for example, their horizon is going to be 180 degrees to the other horizon facing the other way. So we're only ever going to be able to see 180 degrees across a flat surface anyway, no more than that. We also know that a triangle comprises angles totaling 180 degrees. So by just taking a section of this circle, turning it into a triangle, basically half a semicircle, we end up with the same number of degrees as we do in an entire semicircle. And what's very interesting when we do this with a triangle that's 90 degrees here, 45 here, and 45 degrees here, we end up with another triangle from this point to this point, peaking here in the center of, so making these two lines exactly the same length. The angles here are 23.4 and 23.4 degrees here, making this angle something like 130, I think. Yeah, 131 is the angle we get here. And again, this is the angles of perspective that we see here. This declination, if the observer is standing on a flat surface like this declination of perspective is what we see on either side of the observer. And that's compensating for the missing 23.4 23.4 degrees that we have of axial tilt. It's the same here as it is for this triangle that's cut off when we make another triangle of 180 degrees. So let's keep this external frame of reference that's used to model a globe Earth and take the angles here, this triangle that's created with the angles of 23.4 degrees, and apply it to a more local external reference frame. But this time it's representing what the observer on a flat surface sees, and these red lines with angles of 23.4 degrees now represent the angle of declination which the observer would see due to perspective when watching the sun go off into the distance. So if we just have a line here representing where the sun would go above a flat surface, as it goes off into the distance, the observer sees the sun appear to sink down towards his or her horizon. And we can use 23.4 degrees here because we are referring to an external reference frame, and this makes it nice and tidy and malleable for the geometry. We can scale it up and down any way we like. A common mistake often made by people attempting to model sunsets on a flat Earth is that they see that no matter how far away the sun gets from the observer, the angles of elevation never quite reach zero, or the observer's eye level. However, what is being completely ignored is that this eye level is above the surface. So the angle at which the observer sees the sun is going to be different to the angle from which the sun would appear from the surface itself. Here, for example, the observer is looking at a sun at 45 degrees. And this is important because we know that using trigonometry we can measure or calculate the height of something as long as we are the same distance from it as it is high from the surface. The angle of elevation to the top of that object will be 45 degrees for the observer. However, the observer is on the surface, above the surface, and it turns out that when we look at the sun in the sky at about 45 degrees here, the angle from the surface is going to be more like 23 degrees. Again, here is the axial tilt that has been added to the globe because this difference in the observer's perspective and the angle of elevation from the ground is completely ignored. Usually the observer is just ignored as part of the equation, and it's just considered that the angles of elevation are from the ground. But no, there's a difference between what the observer sees and what would be seen from the ground in this orthographic view. So when we factor in another 23%, the sun, 23 degrees, sorry, the sun will eventually reach the eye level or horizon of the observer. So let's take all this geometric modeling that's used to create a globe Earth and apply it to real-life observations that appear to be happening on a flat Earth. This is a photograph of a dam near me. I'm below the wall. We can easily see that with a line representing eye level, which is halfway up the field of view here. Now the camera might not have been completely horizontal, so this might not be a true eye level, but we can see that we are lower than the top of the wall. So the wall cuts off everything in the sky, and it does so quite early. These clouds are not really that far away before they get cut off by the wall. They never actually appear to reach our horizon here. And we know that if something in the sky was going off into the distance, it could be an aircraft, it could be the sun or the moon, the stars, whatever, it will appear to do so at an angle for the observer, depending on the observer's relationship with whatever's in the sky will make a different angle. We know that if, for example, something was going directly overhead or we are at the equator and the sun is going directly overhead, then the only way we can represent it in this two-dimensional photograph of a three-dimensional scene is to have a vertical line going straight down towards our horizon, representing something going off into the distance above us. But usually we'd see some kind of angle like this. So if we add the sun in here, we can see that this is pretty much what we might see from any given location. The angles will vary, but we'll always see the sun appear to sink down towards the horizon as it gets further away. And it doesn't have to get very far at all for it to get cut off, just like these clouds. So this is where demands that the sun should change in angular size really aren't a logical argument, because the sun is, whatever it is, it's a light, it's not a physical, tangible object on the surface of the earth, and it's much, much larger than anything that we can see on the surface of the earth. So here, of course, this wall blocks the sun as it goes off, just as it blocks the clouds. And it doesn't matter how far away we are from the wall, it will always remain its real size, its physical size. But of course, in our eyes, the further away we got from this wall, the more it would appear to get smaller and smaller and smaller, and eventually become part of our horizon. So again, when we're looking across great distances, our horizon comprises all kinds of things on the surface of the earth, much larger and much taller than ourselves, but they just don't appear to have any physical height because we're so far away from them. But they still do the same thing as we see happening here, is that our horizon, the surface rising up to our eye level, cuts off everything in the sky. It's really as simple as that. We see things in the sky traveling away from us, declining towards our horizon. They don't go very far at all until they meet the horizon. Again, their height from us and the speed at which they're going will make a difference to how quickly we see them descend towards the horizon. But that is what they will always do when they go off into the distance. You don't have to be on a sphere for that to happen. We only are told to perceive it and believe it, but it's really just a translation of these angles of perspective and declination that we see happening in the sky, and as we mentioned, on the surface, that bring the surface up to our eye level. So let's just make a few changes and turn this view into an external frame of reference for an observer that will be on the road, on top of the wall here. We'll go to see that in a second. So we'll just take away these, and this is now our side-on view of a flat earth, with an observer on the flat earth up there on the road. So once again, if we take this triangle with the angles of 23.4 degrees that we had left over from our side-on view of the globe Earth, and then used for a side-on view for an observer on a flat Earth, and add it to this scene here. So we can have then an observer up here on the dam, and so as they look across, left or right, across this flat surface, they will see things decline towards the surface, and they will also see in their eyes the surface rise up to their eye level. So in this external reference frame of a flat earth, we have a sun that's going away from the observer, a parallel line to the surface. So here we are now on the road that we were looking at just now. So of course our perspective has changed a lot. We see everything above the surface appearing to sink down towards our horizon, and everything on the surface appearing to rise up to our horizon. We can just stick in some lines here and see that. Yeah, the surface rises to our eye level. We are literally on the ground, so maybe about 3 centimeters above the surface is where the eye level is, and that's where the surface appears to go to, the center of our field of view. And all the angles of everything on the surface going away from us converge here, and everything going away from us in a straight line above the surface converges here. We've got lines following these railings here. This line follows the lampposts up there, and this one follows those railings over there. And we can see that we're very close to these railings, almost underneath them, so we get a very sharp angle here as it goes off into the distance. But these railings here, which are the same height, also parallel to the surface, go off at a very shallow angle because they are further away. So we can represent the sun like this. For me, near the equator, this is what the sun appears to do. It comes overhead and then it appears to set like this, coming down this kind of very sharp angle of declination because I'm on or near the equator. But for someone who is not on the equator, they would see the sun come a much shorter distance above the horizon and a very shallow decline towards the horizon. It all depends again on the time of year and the location, so these angles will change. But essentially we always have this eye level for the observer, and everything below the surface angling towards the horizon. Everything above the eye level is part of the sky, and it comes down to eye level depending on where it is in the sky in relation to us. And this, of course, can be turned into a circle of perspective. So here we have back to the 360-degree globe, split in half by our eye level, so 180 degrees on the top, 180 degrees on the bottom, and these lines then divide the circle up into degrees, which then become triangles. So this can all be translated into a side-on view. We can even scale this up as much as we like. Here it's on a very small scale because we are low to the surface, and we are looking at across these railings go for about half a kilometer. But we can change our view to something much larger, and depending on where you are on the Earth, you will see sunsets do this kind of thing, decline down towards the horizon, or sink down at a much shallower angle the further away you are from the equator. So yeah, this is a very wide view of across the sea, but this is what we would see the sun doing, just as we see angles of perspective here. It's interchangeable, it's scalable. And this is the secret of the deception, using geometry, the geometry of perspective, matching it with the geometry of a globe. But in doing so, this horizontal line of the observer's eye level, when they look straight ahead across a flat surface, has been turned into the actual surface, and a curve has been given to the surface to replace the curve we see caused by perspective in the eyes of the observer. So it is this surface, the fact that the horizon does rise to eye level, has been lost in the translation, as we showed in this image here, with a side-on view of the observer. Again, the angles of perspective that occur across a flat surface with the sun going off parallel to the surface has been converted into an imaginary curve on the surface instead, as we saw with this line here. Yeah? So this curve of perspective has been translated into a curved surface. Again, the fact that the surface rises to eye level at an angle similar to the way we see things coming down to eye level, as we see here, has been converted into a curved surface like this. Any one of us can confirm for ourselves with our own observations that the horizon we see in front of us when we look across a flat surface has nothing to do with curvature. It is an optical phenomenon that is personal to each and every observer. No two horizons are the same. But the height above the surface does make a difference as to how far we can see across the surface. And the distance that we can see across the surface, depending on our height, is the limit where our horizon occurs, and it will create a line that is often just below eye level, but the surface continues on to eye level, but it becomes too indistinct to see properly. So the higher we go, the more detail we can see above a flat surface, and the gaps between objects on the surface appear to get wider and wider until we are high enough to see them properly. As we come down, the horizon remains at eye level, but the surface appears to get more and more compressed, so those gaps between things on the surface will become closer and closer until they cannot be distinguished anymore, simply because we are not high enough to see them properly. And so we do have a horizon that appears on the surface and becomes more and more distinct as we come closer to the surface, and will appear to make the horizon come closer and closer to us the lower we go. Again, it's simply because that is the limit to how far we can see across that surface at such a low level. And I think it has a lot to do with the way light behaves and how it is reflected off the surface into our eyes. So we have this angle of incidence which is just far too shallow for the light from a distant surface to be reflected into our eyes. So it simply becomes invisible, and this is the vanishing point. This is where ships will go sometimes. They do not always disappear from the bottom up. This is just something that can be sometimes observed. Ships will go off on the horizon into the distance and just fade into obscurity, into this nothingness, a point beyond which the light from them is not reflected into our eyes, so we simply do not see them. The same happens to the sun. As it goes away from us, we have lots of clouds in the sky, and eventually it is those clouds in a layer that's much lower than the sun that will cut off the more distant sun. It's very, very simple, logical explanations that work in reality and can be confirmed with a little bit of thought, effort, and some observations. Now, because everything is based on geometry here, it's basically taken the geometry of our spherical eyes, the way we see the world, perspective, which is geometry as we have seen, and used that geometry to create an imaginary globe. However, the mathematics for the distance to the horizon kind of works out. But we know from the observations we made just now, looking at the road on the dam from the side, we know there was no curvature on the surface of the Earth. It was a horizontal, flat surface, albeit rugged. But that is how any natural surface is. We never really experience totally smooth surfaces. But when we were on the road, for the observer on the road, everything that was horizontal and parallel in the side-on view became either declining or inclining to the camera's eye level. And so when I put in the height of the camera, or the camera's eye level, the middle of the lens, as if it's sitting on the ground, it is about 3 centimeters, so 0.03 meters here. You calculate the distance that you should see the horizon, and it is 0.6 kilometers, so about 600 meters, which is about right for that bridge that we were looking across. It's about half a kilometer long, and so we can confirm here that we see horizons across flat surfaces. We know that surface was flat because we saw it from a side-on view. It was horizontal, the lines were parallel, but then we went to the road and made an observation, and we saw a horizon on the road that had nothing to do with curvature. It simply had to do with how high above the horizon of the surface we were. The lower we come, the closer that surface becomes, and then we start to see mirroring on the surface. So the horizon is on the surface. It is going to be either blocked by something taller than you, or it will just be the limit to which you can see across that surface due to things such as the angle of incidence of light or diffraction and other elements and conditions that will affect any observation, making it always unique. But you can generalize with this mathematics that again uses geometry to do this. So just consider this globe represented here as having curvature as the globe of your eyes, and the geometry is exactly the same. It all works out because we're dealing with angles, not necessarily specific measurements, but it is clear that this matches what we can observe across a flat surface. And with that, I'll leave you with some excellent footage by a channel called Wide Awake, and you can see how what we see across this flat road on the dam is exactly the same as what we can observe at sunset. Thank you very much.
And I zoomed in on it, and I wanted to give you a close-up view and a slow motion view of that sun. Now this is the sun, and it's going to slowly disappear. It's going to do a magic act. It's going to do an illusion. It's going to deceive you because it is going to disappear, but it's going to disappear into the atmosphere. Just like some of my boats that I show that get out to a certain point in the horizon, it disappears back into that mirage, that glass area, that mirroring area, that area that mirrors the sky. So again, I'm presenting this to you as my proof. And again, I don't expect anybody to believe me. They don't have to believe me. But this is what I see. So I've got this thing slowed way down. And this is what I want you to see, how this is working. And how where below this, you can see the visible water line. But up above, or above that water line, you can tell that that is a mirroring of the sky. And this is mirrored from the top to the bottom. If you split that in half, it's just mirroring the sun slowly fading away. Now, I am not a professional photographer, but I think that my videos is going to prove to your own eyes what actually happens to the sun. It is a deception. It is an illusion.